So this case, I think we're talking a lot to do with DFS, yeah, DFS. So like without further ado, let's establish every single item. I mean, always introduce a character, and for this case, we are talking about a tree, and it falls under the category of like depth research. Each character is able to cast a spell, and every Leetcode question has its own rulebook, and there's the playout series for this, and we have a core objective for this Leetcode question. So cool. I think the core objective is really comes down to actually finding the smallest value in the array, and for the most part is that how you are able to actually get the smallest value is really understanding of the how tree, the algorithm for tree works. As long as you kind of understand how it goes, you will be able to actually identify, okay, this guy, that's the smallest value. And so we go on to the playout series. So now cool. So I believe the 1 is over here. We have a 2 here and a 3 here. 3 is here. 1 and then the 2. So we are going to, like, what they introduce is using a stack. What they really want to achieve here is like to be able to like iteratively solve this. By iterative, that means just I'm not too sure why they use the term iterative, but we'll see in the playout series, right? So cool. So there's first and foremost the operation z, which is to add the value into the stack first. So I mean, for z operation, it's talking about adding the value to the stack. So cool. Now we always enter towards the left child. I mean, that's for y operation, which is to really, go to the left child, and not only going to the left child, it's really comes down to going as deep as possible. And for this case, it's only coming down to here because it was trying to actually enter to the left again more, but it wasn't able to do so. There's no value over here, so therefore we have like this value, and so we call it we add add it to the stack. Yeah, so we add this value to the stack, And now after we add the stack, we then go to the right child, and then we then remove the last stack. So what happens is that we'll visit the right child, which is a 2. We add the 2 here, and then because we know the moment like we cannot visit the left already and we are going to visit the right, that's when we know that okay, the value is already useless for us, and then we can kind of like remove the last tag, which is this one, and then we go on to the while operation again, visit the left child, and there isn't. So whenever we go to the right child, I think that this is the reference. We take reference for it. Then we move this once, and we go back up. Try to go for the left child. There's no left child. So we can add the stack, but I just believe it added like way earlier, but doesn't matter. I think we can follow this rule as well, like we reference that first, because I think this is much more right. It's because that you always really want to reference it and then you pop. It makes sense, right? So obviously this is removed. The reason why I say that is because that what if there's a value over here? You will add this value first before you add this value. So that's why I argue that you want to put this on, add the value on the later part. So you always try to do reference first before you actually add it. So now we move on. We go to the 2. We try to go to the left child. There's no left child. So we add this towards the stack. Have the 2 here. We go through the right reference, but there's no any item over there. Obvious. That means there's no more item. So therefore, we proceed to remove the last tag, which is 2 for this case. And then now we try go to the left child, but obviously there's no more item in the left child in terms of the perspective of 3. So what it does is that it's gonna be going to the right child reference. It's for this case. and it's gonna try to go to the left, but there's no left, so it's gonna add the current item, which is the 4 over, and doesn't matter like any of these operations because there's nothing else. Eventually what you're gonna do is that you I mean before you go to the 4, actually, because you know this item is the root, so you actually will remove the last tag, which is remove this value before you actually reference into this 4, right? So now you come to 4, obviously no item, you're gonna eventually remove the last tag because you can't move at all. So I think that with that is like the whole of the playout series. And one key thing is that you can see is that there's obviously a lot to do with like multiple operations in like one node. And that it works very logically, intuitively, and I mean that is also one of the fundamentals of having trees. Like the way the maneuver is all very smart maneuvers, smart movements, right? And that falls under the category of like trees. And whatever the Leetcode question is asking, it's asking something that it's they want like the smallest value, like based on the rules of like trees, because the map that we are actually exploring today over here, it's tree, and we want the smallest value. So I mean intuitively you already straight away tell yourself that okay, I need a smart maneuver system, maneuver map around trees, right? So I mean it's already asking a question about trees. Obviously you gotta bring out the character tree to actually solve this, right? So yeah. And you will always think about to use brute force to actually fight the main character over here. I mean the first operation that I actually think of is actually smart maneuver system. Like brute force, you won't be able to actually enter into the system, maybe say operation L, where you know how to actually go towards the left hand side before going the right hand side. Brute force, you only can like just blindly move in this certain direction. And I mean even if the Leetcode question is asking you something about with regards to how to actually smart maneuver like a tree, your brute force isn't up for the job. So I mean with that you're gonna fight against brute force easily out of the water. I think whatever this iterative, whatever they talk about iterative, it I would say that it comes down to whether within like one array that you are able to actually conduct a very multiple filled with multiple simple logic operations, which is for this case I think operation y to o fulfill that criteria. You see over here they just have like um, they want to go to the left child, simple. They want to add an item to the stack, simple. They want to reference towards the right child, simple. They want to remove the item from the last stack, very simple. So it's like a bunch of like simple operations that's been filled up into each node being visited. And by means the multiple simple logic operations, I feel that it just corresponds with iteration as an operation. So whatever iterative means is that you being able to cast these operations of like y to o, it's all filled with simple operations, and iterative it just means that. And where do you actually like to actually conduct iterative operations? In a stack. It's like one of like the suitable place for you to actually conduct that, and I feel it that way after taking a look. So yep, with that everything comes to an end.